So looking at example 8 from the notes, we decided that if we were going to do the Zorro method, that we would have this little nested Zorro method here that we'd have to do off to the side, do it again, bring it back in the fold, and it was too complicated. So in general, if you have a power of x and some repeater there that you can actually call dv, like a sine, a cosine, or an e, meaning you could let u equal x, then the exponent on the x tells you how many subintervals or subnests of the Zorro method you're going to have, and you don't want to have to do that. So if that's more than 1, if that's the squared or higher, then you're probably going to want to do it using the tabular method. So that's what I was in the process of showing you how to do. The tabular method has 3 columns. The first column is u, the second column is dv, kind of the way we normally list them. But then you have a third column that's plus or minus. What that's going to do, it's going to alternate signs. So you still identify what you're going to call u, and you put it here in the first row, x squared. Then you go ahead and just take some derivatives all the way down. In this case, you could stop once you hit 0. X squared, 2x, 2, and 0. Now in the second column, you can do the same thing, but take the antiderivative. The antiderivative of sine is what? The antiderivative is negative cosine, and the antiderivative of negative cosine is negative sine, and the antiderivative of negative sine is positive cosine. Now you could keep going, but maybe stop at this point. If you needed more, you could keep going further. All right, on the third column, it's real easy. You're always going to start with the plus, always. And then you're just going to alternate each row, minus, plus, minus. So here is what Jaime was doing in the show. He was doing tic-tac-toe. You always take your first product down the diagonal, kind of like we do in the Zorro method. So it's going to be a negative x squared cosine of x. And then you go across and you pick up the next sign, which is minus. And then you do it again. You go down the next diagonal, which is going to be a 2x times the negative sine of x. And then you go across and you pick up your next sign, which is plus. And you do it again. Go down the next diagonal, which is 2 cosine of x. And you go across and you pick up your next sign, which is minus. Your next diagonal would be 0 times whatever. Once you hit 0, that's what's nice about using x as u, it's done. So then you can kind of backtrack. You don't need the minus 0. You just put plus c. You don't need the zeros there forevermore. And then, of course, you simplify. Negative x squared cosine of x. This does turn into a plus 2x sine of x. And then a plus 2 cosine of x plus c. So the tabular method works great when you have powers of x. You don't have to do those iterations of the Zorro method, which is a lot to keep track of. So notice we are on our way to getting the right answer. Up here in the purple, we stopped. So the question is, does the tabular method work, or the tic-tac-toe from the movie, does it work every time? Well, let's see. Would it work up here on one of these easier ones? Let's come up to this easy one up here. Does it work on x cosine of x, where the Zorro method works? Let's see. We got u, dv, plus or minus. You have x, that'll be 1, that'll be 0. This is cosine x, that's a positive. This will be sine of x, that's a negative. This will be negative cosine of x, that's a positive. If you go down the diagonal, you get x sine of x. Go across, pick up your next sign, minus. The next diagonal would be minus the negative cosine, which becomes plus cosine. Go across, pick up the plus. When you hit 0, you can just put plus c. Is that the same thing we got over here? Yeah, it is. So does the Zorro method work? Yes, but does the tabular method work? Yeah, they both work. Now what about one of these down here where we couldn't let the x expire to 0? What would that look like? Well, let's try the tabular method. U, dv, plus minus. Those are your columns. Here, remember, we had to let u equal the natural log of x, and dv had to equal x. Well, now, when we take the derivative of this column, we get 1 over x. The next one would be negative 1 over x squared, so on on and so forth. We're not going to hit 0, so we don't know when to stop. So I'm just going to stop there. If I need more, I'll generate more. What's the antiderivative of x? 1/2 x squared. The next derivative would be 1/6 x cubed. Again, I'm not going to stop, so it's going to keep going. Ugh. This will be plus, this will be minus, this will be plus. So here the tabular method's not as nice because you don't expire the left column to 0, but you'll see that Zorro method still does work, and so does the tabular method. You're going to take the first diagonal, 1/2 x squared, natural log of x. Then you go across and you get minus. Now here's the deal. If you kept taking diagonal products, guess what's going to happen? Are you ever going to stop? You're never going to stop. So here's the deal. Once you do your first diagonal product, you could do what I call, you can tie off the process. How do you tie off the process? Well, once you pick up the sign of the next term, after you finish that first iteration, product, pick up the sign of the next term, you tie off with an integral of your horizontal product. Okay, you got to tie it off with the integral of your horizontal product. So here's the minus, put the integral. Now if you go on your next line, which is here, instead of going diagonally, you have to go straight across. There is your horizontal product. So it would be 1/x, 1/2 x squared, dx. And of course, that is the same thing we had right there when we did the Zorro method. So you can use the tabular method every time. You just have to realize, after I take that first diagonal, let me look to tie it off. Can I integrate the horizontal product if it doesn't expire to 0? If you can, tie it off. If not, take another diagonal product, pick up your next sign, look to see if you can tie off the next horizontal product, so on and so forth. So there's that little caveat to the tabular method. Okay, so we just did example 8 with the tabular method, which is what example 9 was asking us to do. I kind of combined both methods, but I never really finished the Zorro method because I wanted to convince you that the tabular method is better. Okay, let's try example 10. Evaluate the integral of t to the 4th e to the 2t with respect to t. What's the method of choice here? Integration by guess and check? Trial and error. By parts. Very good. What are you going to call u? T to the 4th. You want to use the Zorro method? Probably not, because it's going to require 4 nested. That's no way, no how. So let's go to the tabular method. U dv plus minus. And let u equal t to the 4th. So if you have like a power term there, that's real easy. Just go all the way down, expire to 0. 4t cubed, 12t squared, keep taking the derivative, 24t, 24, 0. Nice. And now you're just taking antiderivatives of e to the 2t. And every time you take the antiderivative, you're going to have to do what? Make a correction of a 1/2. Good. So 1/2 e to the 2t, 1/4 e to the 2t, 1/8 e to the 2t, 1/16 e to the 2t, 1/32 e to the 2t, and you could keep going there, but we'll stop because we hit 0 there. And then plus, minus, plus, minus, plus, minus. Alternate signs. Now we're ready to expand it out. Come right here off to the side. It equals the first product along the diagonal is 1/2 t to the 4th e to the 2t. We're going to clean this one up as we go as well. Pick up the sign of the next term, which is minus. The next product is 4t cubed times the 4th, which means it's just t cubed e to the 2t. Pick up the sign of the next term is plus. The next product, 12/8, that becomes 3/2 t squared e to the 2t. Pick up the sign of the next term is minus the product, 24/16. That's going to be another 3/2 t e to the 2t. Pick up the next sign, it's plus. The next product is 24/32, which is 3/4 e to the 2t. And then, of course, if you go across and pick up the minus, your next product is 0 times. So instead of doing minus c, which wouldn't be wrong, we'll just put a plus c. Now that one was pretty easy, relatively speaking, because some of the derivatives didn't have negatives themselves in them. You got to be careful when one of your terms has a negative in it, you know, because the signs change plus or minus, and if there's a negative factor, it'll change the sign. So that makes quick work of something that if you're doing the Zorro method is going to be really confusing and take a whole lot of time. So tabular method. Tick, tack, toe. It's that easy. All right, so far so good. Any questions? All right, example 11. Solve dz dx equaling x cubed natural log of x if z equals 5 when x equals 1. We're solving a differential equation. What should we do first? It's in Leibniz format. Separate the variables, yeah. So x cubed natural log of x dx. Integrate both sides. And what's the antiderivative of the left side? Z. Good. We don't need a plus c. Now the antiderivative on the right, I don't see anything. Integration by parts maybe, huh? U dv plus minus. We'll do the tabular method. What are you going to call u? X cubed? Schroeder, any idea? Yeah? Okay, then we're going to have to find the antiderivative of ln of x. Do you remember what that one was? I don't either. So guess what? We better call u natural log of x and dv x cubed. Not really what I wanted to do, but ln of x kind of forced my hand there, yeah? So there's a plus. All right, so the antiderivative of u, or I'm sorry, the derivative of u is 1 over x, and the antiderivative of x cubed is 1/4 x to the 4th, and that would be a minus. Now, you don't want to keep going too much here, because chances are, if you get two columns and neither one of them goes to 0, chances are you're going to have to tie it off after the first iteration. So generate more if you need to. Let's go ahead and see what we get here. The first diagonal is 1/4 x to the 4th natural log of x. Come across, pick up the sign of the next term, which is minus. Now look to see if you can tie off the horizontal product. It'd be 1x times the 4th x to the 4th, which would end up being 1/4 x cubed. Do you know how to integrate 1/4 x cubed? Yes. So there you go. You tie it off with an integral. You still picked up the minus, tied it off with an integral. So really what we did is we did the z method there, but we did it out of the table. And so there's still one thing left to evaluate. So whether you want to use the z method there or the table, it's up to you. We end up with a 1/16 x to the 4th plus c. Now that is the general solution. It's solved for z in terms of plus c. Now I have to find the particular solution. So we'll say at the point 1, 5, showing that we're plugging in, 5 would equal 1/4 times the natural log of 1 minus 1/16 plus c. What's the natural log of 1? 0. So we end up with 5 plus the 16th, which is the same as 81/16. So our particular solution is z equals 1/4 x to the 4th natural log of x minus 1/16 x to the 4th plus 81/16. So reviewing solving a differential equation, but in the context now of the integration technique being integration by parts. Yes? Where did the 1/4 x cubed after the integral come from in the second line? Where did that come from? Oh, this is, you take the horizontal product right here. When you tie it off with an integral, you take the horizontal product. So that's going to be 1x times 1/4 x to the 4th. this x and this x to the fourth divide out to give you 1/4 x cubed? Good question. Any other questions on the tabular method? It's a gimmick. It's an organization tool. And so you have to kind of learn its limitations, you know. And one of the limitations is when it doesn't expire down to 0 in one of the columns, you look for your diagonal product and then look to tie it off horizontally right away. Or just use the Z method. The tabular method really is nice if you have a variable to a power in the left column and you're able to go all the way to 0. Okay, example 12. I'm going to let you do this one. See if you can figure it out. Here's our function. I want you to find the average value on the interval from 0 to pi halves. Find the average value from 0 to pi halves. I'll give you a minute or two. Ready to go over it? Maybe you're stuck.